Hello and welcome back to this new series of lecture videos which will cover the applications of some of the popular transforms that are used in engineering. I made some earlier videos relating Laplace transform with the Z transform and Fourier transforms and so on. But the focus of this series of videos would be on what is the application of these transforms. Of course, we have seen several videos and several lectures available on how to compute these transforms. But what is more important is what information do these transforms give us, and how does these transforms allow us to understand the signals or systems for which these transforms are being computed. So I'm going to begin by talking about the Laplace transform. Of course, we are not going to do any computations of the Laplace transform itself, but our focus here would be on understanding how the Laplace transform is used for the analysis of signals and systems. And in particular focus here would be the region of convergence. So we are going to talk about what is the region of convergence for the Laplace transform, what do we mean by the region of convergence, and what does the region of convergence look like for different kinds of functions. So Laplace transform basically converts a function of a real variable to some function of a complex variable. So for example, we could have a time domain signal, which is a function of time, which is converted to the Laplace domain as a function of a complex variable, normally denoted by the variable s, where s is a complex variable. And Laplace transform has wide applications in engineering, and as I mentioned earlier, it is used to analyze and design signals and systems. And in this video we will see what is the region of convergence, and we want to develop a general understanding of what the region of convergence looks like for different types of signals. Another important aspect of the Laplace transform that we will highlight here is that the algebraic expression for the Laplace transform may not be unique in the sense that multiple signals may have the same algebraic expression for the Laplace transform. However, what distinguishes the signals is the region of convergence for the Laplace transform. So we might have two different signals whose Laplace transform expressions are identical, but they will be distinguished only by the difference in their region of convergences. So therefore, it is necessary that when we mention the Laplace transform of a function, we should also specify the region of convergence for the corresponding Laplace transform. So the algebraic expression alone is not complete in terms of expressing the Laplace transform of the function. We should specify the Laplace transform along with this region of convergence. So let's quickly highlight what does the Laplace transform function look like. So the Laplace transform is defined by this integral, where we take the function of time, a function of a real variable denoted by x of t here, and compute this integral by multiplying the continuous function with e power minus st, where s is the complex variable. So this integral here is what gives us the Laplace transform, and the variable s is a complex number denoted by sigma plus j omega, where sigma is the real part of that complex number and omega is the imaginary part. And the region of convergence by definition is nothing but the region in the s-plane. So this plot that we make with sigma on the x-axis and j omega on the y-axis, that is the real part of s on the x-axis and the imaginary part of s on the y-axis. This region is where we will plot the Laplace transform. And for a given function, the Laplace transform integral may not converge in the entire s-plane. It might have specific regions within the s-plane where the integral converges. For regions outside that region, the integral may not converge. So the region of convergence is basically the range of values of the complex variable s for which the Laplace transform or the Laplace integral converges. For other regions, the integral would compute to be beyond the bounds. That means it will compute to infinity. So therefore, the Laplace transform does not exist in those regions. So the region of convergence is basically the range of values of s for which the Laplace transform converges. So the complete representation of the Laplace transform should include the algebraic expression for the for this integral x of s along with the region of convergence. If we specify only the expression for x of s, it is incomplete. We need to specify along with x of s the region of convergence for x of s as well. Okay, now let us look at the specific signal here. Again, we are not going to go into the workings of the integral itself, but rather our focus will be on the region of convergence. There are plenty of videos available online where the computation of the integral is demonstrated with significant detail, so we will not go into those aspects of it, but the focus here would be on understanding what is the region of convergence for the given signal. So if you look at the signal here, the x of t that we are concerned with is e power minus 8. It's an exponential signal multiplied with the u of t, which is unit. So that means this exponential signal is a causal signal. Its value is non-zero only for positive values or non-negative values of time. For negative values of time, the signal is 0, and we compute the Laplace transform by applying the Laplace integral. And if you notice here, the Laplace integral, which extends from minus infinity to infinity, now becomes 0 to infinity because the signal e per x of t is 0 for negative values of time. So therefore, the integral that we compute here is only for those values of time for which the signal x of t is defined. So we have it only from 0 to infinity. And when we compute this integral, we get x of s in this particular form. X of s is 1 over s plus a, where s is sigma plus j omega. So when you substitute s as sigma plus j omega and divide it into the real and imaginary parts, so we get it as 1 by sigma plus a plus j omega. And this integral converges for the condition that sigma plus a is positive. In other words, the sigma value is greater than minus a. When we take this a to the other side, we get sigma greater than minus a, or we also say that as the real part of s is greater than minus a. And this is the region in the s-plane for which the algebraic expression for the Laplace transform x of s converges. So in this case, it is the region in the s-plane to the right of the line sigma equals minus a. So we have this red line here denoting the point sigma equals minus a. So we have this line passing through the point sigma equals minus a, and the Laplace transform converges for all values of s when the real part of s is to the right side of this line. So in other words, for sigma greater than minus a. So one of the observations that we see here is that when the signal is right-sided, as in this case, the signal is defined for, extends to infinity towards the right side. In this case, we see that the region of convergence is some region to the right of some point for the value of sigma. Okay, it's on the extending to the right side of some point sigma equals minus a. Okay, so that's the first observation we make here. So let's move on to another example here, and we will choose, in fact, we'll use the same example, but we'll now consider the function x of t for different possible ranges of a. What happens when the value a is positive? So when the value of a is positive, we'll have e power minus at. When a is positive, this will be decaying exponential. So in this case, the expression is same, 1 by s plus a, and sigma greater than minus a is the region of convergence. So because a is positive, minus a lies to the left of the origin, and this line here is on the left hand side of the y-axis or the j omega axis. And what we notice here is that in this case, when when a is positive, the region of convergence includes the j omega axis, and this is significant. When the region of convergence includes the j omega axis, this gives us further information regarding that particular function or signal x of t, and that is that we will be able to compute the Fourier transform for that signal x of t as well, because if you look at another video that I made earlier relating the Laplace transform and the Fourier transform, you'll notice that the Laplace transform, when evaluated on the j omega axis, gives us the Fourier transform. So therefore, if the region of convergence for the Laplace transform includes the j omega axis, then for that signal we could compute the Fourier transform as well. So that means we can compute the Laplace transform at sigma equal to 0. That means we are going to evaluate the Laplace transform along the j omega axis. That's what happens when we make sigma equal to 0. And when sigma equals 0, what we are basically getting is the Fourier transform of the signal. So Fourier transform is nothing but the Laplace transform evaluated along the j omega axis. And when the region of convergence includes the j omega axis, then it guarantees that the Fourier transform for that signal exists. Now, it could be true that for certain special functions, the region of convergence of the Laplace transform does not include the j omega axis, but the Fourier transform of that function still exists. So we can't generalize that, but more often than not, we can say that if the region of convergence for the Laplace transform includes the j omega axis, then the Fourier transform for that signal could exist. Okay, now let us see what happens when the exponent a is negative. So the expression for the Laplace transform is going to look the same, except for the fact that the region of convergence is still sigma greater than minus a, but when a is negative, this becomes sigma greater than negative of negative a. That means sigma greater than positive a. That means the region of convergence is going to be the region to the right side of the line sigma equal to a. So if you notice here, the point sigma equal to a is to the right hand side of the origin, and the line which passes through that point is parallel to the j omega axis, to the right side of the j omega axis, and the region of convergence is the region in the s-plane to the right side of this line. So therefore, what we notice now in this case is, for this particular signal e power minus at, when a is negative, when the exponent a is negative, the region of convergence does not include the j omega axis. So that means because the region of convergence does not include the j omega axis, the Laplace transform cannot be evaluated at sigma equal to 0. That means we cannot evaluate the Laplace transform along the j omega axis. So therefore, for this particular case, the signal x of t, that is when a is negative, the signal x of t has a Laplace transform, but since the Laplace transform's region of convergence does not include the j omega axis, the Fourier transform for this signal does not exist. That is when a is negative. So the region of convergence gives us an idea of, when we know the region of convergence of the Laplace transform, it would give us some kind of indication whether the Fourier transform for that signal would exist or not. Of course, we can't generalize this. There are special cases of signals where the region of convergence of the Laplace transform may not include the j omega axis, but still the Fourier transform for that signal could exist. And one classic example of that is the unit step function itself. But we'll come to that in more detail in subsequent videos. But for now, let us just focus on where the region of convergence lies in the S-plane for different values of A and for different types of signals. Okay, so for a right-sided signal, we saw earlier that when A is positive, the boundary line was parallel to the j omega axis and to the left of the j omega axis, so the region of convergence included the j omega axis. When A is negative, then the boundary line for the ROC is towards the right of the j omega axis, and therefore the j omega axis is not included in the region of convergence. Now let's see what happens when the exponent A is equal to 0. So when we put A equal to 0 for our signal x of t, this e power 0 is 1, and what we get is just u of t, which is nothing but our unit step signal. So in that case, what we are basically computing is the Laplace transform of the unit step function. And it turns out that the Laplace transform of the unit step function is 1 upon s, and the region of convergence for that is the real part of s being positive. So that is sigma greater than 0. So again, what we see is that the boundary line for the region of convergence is the j omega axis itself. So the entire region in the S-plane to the right side of the j omega axis is the region of convergence for the Laplace transform of the unit step function. Now notice here that the region of convergence is sigma greater than 0, not equal to 0. Sigma equal to 0 is when the j omega axis is included in the region of convergence. Here that is not the case. Sigma equal to 0 is not along the region of convergence. That means the j omega axis does not lie in the region of convergence of the Laplace transform for the unit step function. However, as I mentioned earlier, the unit step function does have a Fourier transform. So having the j omega axis in the region of convergence is not a necessary condition for the Fourier transform to exist. It is just a sufficient condition. So therefore there can be certain signals for which the region of convergence does not include the j omega axis, but its Fourier transform still exists, as in this particular case. Okay, so even though the region of convergence for the Laplace transform of the unit step function does not include the j omega axis, it is the entire region to the right of the j omega axis, but not including the j omega axis, the Fourier transform of the unit step function exists. Okay. Now let us look at specific examples with some numbers. Okay, instead of a generally is writing it as a, we have put the value of a equal to 1 here. So it's e power minus t u of t, in which case the Laplace transform is 1 over s plus 1, and its region of convergence is the real part of s being greater than minus 1, that is sigma greater than minus 1. So the boundary for the region of convergence is the line passing through the point sigma equal to minus 1, and all points of s lying to the right side of this line constitute the region of convergence for this particular Laplace transform. Similarly, when a equals 2, we have the Laplace transform as 1 over s plus 2, in which case the region of convergence is to the right side of the line passing through sigma equals minus 2. So we are now looking at these two signals individually. Okay, this signal e power minus t u of t has a Laplace transform given by this expression 1 upon s plus 1, with its region of convergence to the right side of sigma equals minus 1. Similarly, for e power minus 2t u of t, the Laplace transform is 1 over s plus 2, with its region of convergence lying to the right side of sigma equals minus 2. Now let us combine these two individual signals and constitute one signal which is a linear combination of these two individual signals. So We had e power minus 2t u of t and e power minus t u of t in the previous slide. So we are just making a new signal x of t, which is some linear combination of these two signals. And we want to find what is the region of convergence of this overall signal x of t, which is a linear combination of these two individual signals. So for e power minus 2t u of t, the Laplace transform we saw in the previous slide is 1 upon s plus 2. So that signal, when it is multiplied by 3, we get the Laplace transform of it as 3 upon s plus 2. Similarly, for e power minus t u of t, the Laplace transform is 1 upon s plus 1. So therefore, for 2 times e power minus t u of t, the Laplace transform is 2 times s plus 1. So combining these two in a linear fashion gives us the Laplace transform of the linear of the combined signal, whose Laplace transforms are also combined in the same linear fashion, and that also exhibits the linearity property of the Laplace transform. So this is the overall expression for the Laplace transform, which we can take the LCM for this and combine it as, and have it as this expression. And how do we find the region of convergence for this overall signal? So we know that for the first component, the region of convergence is to the right side of the line sigma equals minus 2. So that's the blue region here is the region of convergence for the first component here. Okay, that's the blue region here, to the right side of sigma equals minus 2. And for the second part of the Laplace transform, the region of convergence is to the right side of sigma equal to minus 1, which is depicted by this pink region here, to the right of the line sigma equals minus 1. So we know the region of convergence is for the individual components. So what is the region of convergence for the overall signal x of t, which is a linear combination of both these signals? And what we find is that the region of convergence is nothing but the intersection of the region of convergences of the two components. So the region that is common to both the ROCs of the two individual components, so ROC1 is the region of convergence for the 1 upon s plus 2 component, and ROC2, which is the pink region here, is the region of convergence for the 1 upon s plus 1 component. So the overall region of convergence is going to be the intersection of both these regions, which is the common area belonging to both the regions, which is the shaded area shaded region shown by these shading in the slanted lines here, the red region here. So that is the overall region of convergence for the combined signal x of t, which is the region of convergence which is common to both the ROCs of the individual components. So therefore, the common area is the area to the right of the line sigma equals minus 1. So this entire region to the right of sigma equals minus 1 is the combined ROC for both the components. So the signal x of t, which is a linear combination of these two individual components, has an ROC which is to the right of sigma equals minus 1. So what we notice is that all the signals that we have taken in these examples, they are all right-sided signals. That means you see that we have multiplied them with the unit step signal. That means they all extend to the right until infinity. So they start at some point and extend to the right until infinity. So we call them as right-sided signals. And what we notice for such signals is that all right-sided signals have region of convergence which is lying to the right of some sigma value. So the ROC is lying to the right of some sigma greater than sigma naught. In this case, sigma naught is minus 1. So we refer to this ROC as the right half plane. So right-sided signals have ROCs which are commonly referred to as right half planes. So basically the ROC extends to the right of some line parallel to the j omega axis. Okay, extending this, we can now think about what does the ROC of a left-sided signal would look like. So intuitively, you can say that for a right-sided signal, if the ROC extends to the right of some line sigma, then for the left-sided signal, the ROC would extend to the left of some line passing through some value of sigma, right? So let's look at these two examples of signals, and when you evaluate the Laplace transform for both these signals, you will find that the algebraic expression for the Laplace transform in both the cases are identical. So we have on this side the left-sided signal, which is extending to infinity towards the left, and we have this signal which is right-sided. That means the signal extends to infinity towards the right. The algebraic expression for both these signals is 1 upon s plus a. The only thing that differs is their region of convergences. For the right-sided signal, the region of convergence is lying to the right side of some line sigma equals minus a, or for values of sigma greater than minus a. For the left-sided signal, the region of convergence is lying to the left side of some value sigma equals minus a. That means for values of sigma less than minus a. So when we look at these in the S-plane, for the right-sided signal, the ROC is extending to the right side of some line passing through sigma equals minus a, and the ROC for the left-sided signal is lying towards the left side of some line sigma equals minus a. So for a left-sided signal, the ROC is to the left of sigma equals minus a, and for the right-sided signal, the ROC is to the right side of sigma equals minus a. Or in other words, what we can deduce from that is the fact that for right-sided signals, the ROC is extending towards infinity on the right-hand side, and for the left-sided signal, the ROC extends towards infinity on the left-hand side. So for the right-sided signal, we refer to the ROC as the right half plane, and for the left-sided signal, we refer to the ROC as the left half plane. So this is the general idea we should have. By looking at the ROC, it gives us an idea as to what the signal is going to look like in the time domain, in which direction the signal extends. So if the ROC of a particular signal is extending towards the right of some line, it tells us that the signal is right-sided, and if the ROC of the Laplace transform of a signal is extending towards the left side, then the signal is a left-sided signal. Now, what happens if the signal is two-sided? That means the signal is extending to infinity on both the sides. So it is going to infinity on the right side, as well as it is extending to infinity on the left-hand side. In this case, what do we think is going to be the ROC for this particular signal? And to understand that, we are just going to break up this signal, which is two-sided, into two components. One component is the right-sided component, so that means that we are breaking up the signal to extend to start from t0 and go to infinity on the right side. So that's a right-sided component. And then the second part of the signal is the left-sided component, which lies to the left side of this t0. So we have this left-sided component. So obviously, the right-sided component is going to have an ROC, which will be the right half plane, and the left-sided component will have an ROC, which will be the left half plane. So that means the component xr of t, which is the right-sided component of the signal x of t, consists of the region of convergence extending to the right of some sigma equals sigma r. That could be any value sigma r. Similarly, the left-sided component will have the ROC lying to the left side of some sigma equals sigma L. So that is the individual ROCs of the right-sided component and the left-sided component. So what will be the ROC of the combined two-sided signal? So the ROC of the combined components, that is the two-sided signal, would be the overlapping region of the ROCs of the right-sided component and the left-sided component. And this is what the this is how we would be able to intuitively deduce what is the ROC for the two-sided signal. So let's look at it on the S-plane plot. So for the right-sided component, the ROC includes the region to the right of sigma r. So sigma r is some value of sigma, and ROC is extending to infinity towards the right hand side of sigma r. Similarly, the ROC for the left-sided component is going to be extending to negative infinity towards the left side of sigma l. So this region here extending towards the left side of sigma l is the region of convergence for the left-sided component. So what is the overall region of convergence for the two-sided signal? So it is going to be the overlapping region between the ROCs of the right-sided component and the left-sided component. So the pink region here is the ROC of the right-sided component. The blue region here is the ROC of the left-sided component. So the ROC of the two-sided signal will be the overlapping region of these two ROCs. So the overlapping region is this region between these two lines, extending from to the right of sigma r and up to sigma l. So it's between sigma r and sigma l. So it's the region of the S-plane which lies to the right of sigma r and to the left of sigma l. So it has two boundaries, one to the left, which is sigma r, and the other to the right hand side, which is sigma l. And in this case, what we notice is that there is an overlap existing, because we have taken the sigma r, we have taken in this example that the sigma r, which is the boundary for the ROC of the right-sided component, is smaller than the boundary of the ROC of the left-sided component. So sigma r is less than sigma l, in which case we get an overlap between the two ROCs. So it is this region here between the two lines which will be the ROC of the two-sided signal. So we see here this shaded region here is the ROC of the two-sided signal, which is this strip in the S-plane between sigma r and sigma l. Okay, so what happens if sigma r is greater than sigma l? That means the boundary for the right-sided component is greater than the boundary for the left-sided component. Let's see what happens in that case. So we have sigma r here and sigma l over here, and clearly sigma r is greater than sigma l. So that means the ROC for the right-sided component is lying to the right side of sigma r. The ROC for the left-sided component is lying to the left of sigma l. And when we look at it combined in a single S-plane diagram, so we have this pink region here, which is the ROC for the right-sided component, and the blue region here, which is the ROC for the left-sided component. So the ROC for the two-sided component will be or should be the overlapping region of these two ROCs. And clearly in this case, there is no overlapping region between the ROCs of the left-sided component and the right-sided component. So what it means is that for the two-sided signal in this case, the ROC does not exist for the Laplace transform. So that means the Laplace transform does not exist for this particular signal x of t, because its left-sided component ROC and the right-sided component ROC have no common areas. So therefore there is no overlap between them, and therefore there is no region in the S-plane where the Laplace transform or the Laplace integral of the two-sided signal converges. So therefore we say that the Laplace transform does not exist for that particular signal, and this is true when sigma r is greater than sigma l. So what we notice here is that even though the ROC exists for the left-sided component and the right-sided component, there is no ROC for the overall two-sided signal x of t. So therefore there is no region in the S-plane where the Laplace transform of x of t converges, and hence we say that the Laplace transform does not exist for the signal when sigma r is greater than sigma l. Okay, now let's look at another type of signal where we have a signal of finite duration. So far what we have seen are signals of infinite durations. So it was either a right-sided signal extending to the right to infinity, or it was either a left-sided signal extending to the left towards minus infinity, or it was a two-sided signal where it was extending to infinity on both sides. So we have seen those cases so far, but now let us look at the Laplace transform ROC for a signal which is of finite duration, and for a signal which is not just for finite duration but also absolutely integrable. That means when we integrate the signal between its limits, it remains bounded. Okay, the integral is not infinite, so we say that it is absolutely integrable. In which case, what is the region of convergence? For a finite duration signal, where the duration of the signal is for a finite amount of time, and when the signal is absolutely integrable, the ROC is the entire S-plane. That means the Laplace integral converges for any point in the S-plane. So we can have S to be any point in the entire S-plane, and the Laplace integral converges. So we say that the region of convergence for such a signal is the entire S-plane. So again, when we find the Laplace transform of a signal and find that the signal is the ROC is the entire S-plane, it gives us that the signal is of finite duration and it is absolutely integrable. Again, this is useful when we have a function which is representing the impulse response of some system, and we can deduce whether the system is stable or not. So it gives us an indication but just by looking at the region of convergence of the Laplace transform. So for a finite duration signal which is absolutely integrable, the ROC of the Laplace transform is the entire S-plane. So to summarize, we have seen the signals of different types. Okay, the first is we have seen signals which are right-sided, left-sided, two-sided, and finite duration signals. And in all these cases, when we look at the Laplace transform, what we notice is that the Laplace transform's ROC is in the form of rectangular strips which are parallel to the j omega axis. So it could be a strip parallel to the j omega axis starting at some points to the right of some line parallel to the j omega axis and either extending to infinity on one side or the other, but in general it's a rectangular strip parallel to the j omega axis. Or in the case of the two-sided signal, we had a situation where it was a rectangular strip bounded on both sides by some lines. So in general, what we notice is that the ROC of the Laplace transform consists of strips which are parallel to the j omega axis. And then we also saw that when the signal x of t is of finite duration and absolutely integrable, then the ROC is the entire S-plane. So the Laplace integral converges for any value of S. Then we saw what happens when the signal is right-sided. In this case, the ROC is the right half plane of the S-plane. That means the ROC extends to the right side of some line sigma equal to sigma naught. And similarly, for a left-sided signal, the ROC is the left half plane, which is nothing but the ROC extends to the left side of some line sigma equal to sigma naught. Okay, sigma is nothing but the real part of S, right? So for some line sigma equal to sigma naught, the ROC extends to the left of that line. And when we have a signal that is two-sided, then the ROC would be bounded on both sides. On one side we will have sigma r, and on the other side we will have sigma l, and so the ROC would look like a strip which is parallel to the j omega axis. Of course, this will be a strip only when the the boundary line for the right-sided component is smaller than the boundary line for the left-sided component. Otherwise, there will be no overlap between the ROCs of the right-sided and left-sided components, and therefore there would be no overlap for the overall component. So therefore there will be no common area where the Laplace integral converges, in which case the two-sided signal will have no Laplace transform. So we have a general understanding now of what the ROC looks like for different types of signals, and we have not gone into the details of how to compute the Laplace transform itself. Our focus here has been only to get a high-level understanding of what the ROC is and what it looks like for different types of signals, and we are going to just extend this idea further, where we will now introduce in subsequent videos the concept of poles and zeros for the Laplace transform, and relate how the ROC is is in relation to the poles and to the position of poles and zeros, and thereby we will try to deduce certain properties about the function for which we are computing the Laplace transform. And thereafter what we will do is we will show the relationship subsequently between the Laplace transform and the Z transform, and make a one-to-one comparison between the ROC for the Laplace transform and the ROC for the Z transform, and we will try to understand what is the mapping between the Laplace transform and the Z transform, both in terms of the ROCs and also in terms of the locations of the poles and zeros, and how this information that includes the ROC along with the positions of the poles and zeros allows us to deduce certain information regarding the characteristics of the function or signal or the system that function is representing. Okay, we'll stop here for now, and we will continue in the next video, where we will take this idea of ROC a step further by including the discussion on poles and zeros as well.